Any questions? All right. Seems like we left off with looking at the gravitational forces between two masses. I believe that was this group. I got a nod there, so all right. Assuming Benjamin is all known. All right, let's find the mass of the Earth. And to do that, all we need is some satellite orbiting the Earth, and the Moon is, we've probably had more observations about the Moon than other satellites about the Earth. So, and we will assume a circular orbit. Now, if you've looked at the videos, there's a section where I do the full derivation and the elliptical orbit a little bit, but in essence, to derive Kepler's laws the right way. I do it in a slightly simplified version, and then I have one video at the end where I go, all right, technically you shouldn't have been using that mass, you should have been using this mass, but everything else works the same. All right, let's go through the process. Force diagram. What are the forces acting on the Moon?
Gravitation.
Okay, acting which way?
Towards the Earth.
Not putting W because weight doesn't make a whole lot of sense in this context. All right, what else? Go down our checklist here. Gravitational force. We got normal force. Why not?
Not touching anything.
Okay. Other? Tension? Friction? All right, so that's it. Coordinate system? Sorry, what's the direction of acceleration for something traveling in a circular orbit?
The center of the circle.
Say it again?
The center of the circle.
Indeed. So my acceleration is in that same direction. So we're going down our process here. Now coordinate axes. How should we set up our positive directions? Or singular, probably. What do you want to make the positive direction?
The center of the Earth. The center.
It's not really a direction, that's more of a position.
Like that way.
Okay, same direction as acceleration?
Yeah.
Okay. It's a one-dimensional problem, even though it's traveling in 2 dimensions, but if we're taking a snapshot here, it's a one-dimensional problem, so I can just make that the positive direction. Or technically it's the negative bar hat direction, but making that the positive direction makes sense. Decomposition, do I have to break up my force vector? All right, got 2 people saying no. All right, we're up to 3. And 4, we got a unanimous. All right, equations of motion. What is the equation of motion? And again, F equals ma is our template. In unison would be really cool right now. What are all the forces acting in the positive direction?
Acceleration. Acceleration.
Forces.
Force of gravity.
Yeah, that's it. That's equal to the mass of the Moon, put a little m down there, times the acceleration. What kind of acceleration is this going to be?
Centripetal.
All right. Substitution now. Do we have an independent formula for any of these things?
No.
Gravity.
Acceleration.
Those two. What's the independent formula for the force due to gravity? The answer was yes, by the way.
It was like some constant times the masses over something, the radius or something,
Radius of what?
the orbit.
Yes. The orbital radius squared.
No.
So mass of the moon, so gravitational constant, mass of the Earth, mass of the moon, times the orbital radius, so the Earth moon orbit squared. And that's equal to the mass of the moon times, what's the formula for centripetal acceleration?
Velocity squared over radius.
Speed squared.
Okay.
Always that from a semantic point of view, technically when you're squaring a vector, you're doing a dot product with itself, and I think you can make an argument that velocity squared and speed squared are the same thing. However, speed. All right, now let's solve. We're trying to find the mass of the Earth, so ultimately we're going to get it in terms of that. Can we get rid of anything?
Do we divide both sides by the mass of the moon?
We sure can. So mass of the moon goes away.
Maybe cancel one of the R's on the left and get rid of the right one.
Because this is the radius of the circle that the moon is traveling in, and this is the distance from the Earth to the moon, center to center. So they are indeed the same. So we can get rid of that and that. So we're now down to Excel. Come on. The gravitational constant times the mass of the Earth over the orbital radius is equal to the speed squared. That is a sad looking R there. And I'm not convinced that's much better, but. So how do we find speed? Flashback. Basic definition of speed.
Speed, time, or distance over time.
Yes, distance over time. So this is just the distance that it travels divided by the time squared. Now, as long as the force is perpendicular to the motion, because remember that this wants to travel in that direction, that's the direction of the velocity at that moment. The force is perpendicular to it, so there will be no change in speed. In order to have a change in speed, some component of the force must be in the direction of the velocity or opposing it. But perpendicular, all that's going to do is direction will change, speed will stay the same. So if we think about going around the Earth once, what is the distance, formula-wise?
The circumference.
And what's the formula for that?
2 pi r.
So this becomes 2 pi r over, since we're talking about going around once, we use a capital T. Have we dealt with capital T before? I think this is the first time. All right. Capital T, and the reason why I don't use capital T for tension is the period. And it is the time to complete one cycle of repetitive motion. And I think, hopefully that we can agree that the moon does go around the Earth on a regular basis. So this capital T is for the period. It is a time specifically for going around once squared. And so what I have now is 4 pi squared r squared over t squared. And I have that r down there, so what I'm going to do is just do a little cross, well, I'm solving for mass of the Earth. So taking that and that into account, what's the formula for the mass of the Earth?
Pi squared r over gt squared.
What's the mistake?
Would it be R cubed?
R cubed.
Oh,
Yeah, we're not canceling out there. All right, so we now have our formula for the mass of the Earth. And the reason why I feel like this is legitimate to stop here, because we could have, knowing what the speed of the moon is, probably not as, that's not the kind of thing that you find in the textbook easily. So the distance to the moon has been studied for centuries, millennia. So that distance is well known, as well as with observations, we know how long it takes to go around the Earth. So 4 pi squared times that distance, which there we go, 3.84 times 10 to the 8th. Divided by 6.67 times 10 to the negative 11 times the period. Well, let's do a little math over here. The period, anyone know roughly the period of the orbit of the moon?
It's close to a month or something.
Yeah, it is close to a month. 27.3 days. And since we're dealing with G is in the standard units, this is in standard units, that's meters. It's actually stick units in here. That's meters, so we'll get a meters cubed. This is Newton meters squared per kilogram squared. In essence, what I'm getting towards is that the period really should be in seconds. So how do we convert that into seconds?
Multiply by 24, and then 60, and then 60, and then.
So 24 hours per day times 60
Minutes per hour,
minutes per hour.
and then 60 seconds per minute.
And if in doubt, just make sure that we can cancel out units. So we have day, hour, minutes, we'll up to seconds. And what is the period of the moon in seconds?
$2,358,720.
Did I write it down correctly?
Yeah.
Okay. So 2, 3, 5, 8, 7, 2, 0 squared. And if we crank through all that,
6.0. How many places do you want it out to?
The right amount?
02.
Go to, alright. Either of you get the same thing? Or any of the three of you get the same thing? Or do we have 4 different answers?
I ended up with 40 million. 40,851,908.
Which is way too many places, but whatever.
That's quite a difference there.
Forgot to cube that top one.
Oh, you didn't cube it?
Now I have 2 million. Wait, no, that's literally the same thing as the.
Alright, while he's figuring that out, Osama, did you come up with a third answer?
I guess, 7.905038063 times 10 to the 43rd.
Chance?
Getting there.
We got a 3-way tie here.
Now I got 6.023 times 10 to the 24.
Alright, so you now got that one instead of that. So you're either both right or you both made the same mistake. Which is that? Now, one of the reasons why I want all of you to do this is when dealing with the times 10 to the, sometimes people put in an extra 10. And why in the syllabus, I put in there, you need a calculator which you know how to use. Do you have trouble reading?
A little bit.
Which,
Just the bottom right.
this number right here?
Yep.
2358720. You want me to read it again?
No, I got it. Okay, I got the same.
You got the 6.02 times 10 to the 24th?
Yep.
So Osama, you're daring to be different.
I got the same one again.
You got this one again?
Yeah, no, the top one again.
You got
The 6.02.
that one?
Yes.
It should be the 6.02 times 10 to the 24th. Trying to think of how you get, oh. No, that would go the wrong way. exponents could mess you up.
Forty cubed for 64.
No, that wouldn't explain it. Oh, 1, 2, 6. Having a division in the wrong spot could also mess it up. All right. Units?
Kilogram?
Is that kg question mark? You wanna say it with confidence, or do you wanna keep the question mark there?
I'm pretty sure it's kilograms.
How would Mr. T say it? I'm getting a blank clip. Either you don't know who Mr. T is, or you just don't wanna do a Mr. T imitation.
Well, it's the former.
Ask your parents.